Try to define a complex, curved 3D surface using traditional coordinate dimensioning, and you end up with a mess. You must pile on overlapping x and y coordinates, specific radii, and angle dimensions just to approximate the curve you want the machinist to hit. We can strip away all that ambiguity. All of those messy coordinate dimensions can be completely replaced by a single profile of a surface feature control frame. There are two profile symbols in GD&T. Profile of a line evaluates a specific 2D cross-section, but profile of a surface takes that logic into the third dimension. It controls the entire continuous face of the part, ensuring the entire physical shape matches your intent. To do this, the profile symbol relies on the true profile. This is the mathematically perfect, exact nominal geometry driven directly by your 3D CAD model. Standard plus or minus tolerancing fails on functional 3D shapes, like aerodynamic wings or ergonomic handles, because a single linear measurement can't capture a continuous sweep. Profile of a surface anchors manufacturing requirements directly to the exact 3D geometry of the design. When applying a profile of a surface tolerance, you generate a strict 3D boundary. Two virtual planes project outward, creating a dimensional sandwich around the true profile. For a part to pass inspection, every microscopic point must fall entirely between these boundaries. By default, this bilateral zone is distributed equally. This drawing shows how we override that default. The right panel includes a circle U symbol inside the feature control frame. This unequal disposition modifier allows you to shift the entire tolerance zone to one side of the true profile, dictating exactly where material can be added or subtracted. Shifting this 3D boundary is a critical tool for parts that have to fit closely together. If a curve is designed to sit flush against another component, allowing excess material to build up on the outside of the profile will prevent the parts from assembling. Without datums, profile only controls the form of the surface. It verifies the shape is correct, regardless of location or orientation. But watch when we add datums A, B, and C. The tolerance zone snaps into a rigid position against the datum reference frame. The symbol now does three jobs at once, simultaneously controlling form, orientation, and location. Take a moment to think about this. If you see a profile of a surface callout on a drawing that is fully constrained with three datums, what exactly is that symbol controlling? It dictates form, orientation, and location, all at the same time. You can use it as a simple shape checker without datums, or you can use it to rigidly lock a complex curve into a specific coordinate space. This flexibility is what makes profile of a surface so versatile. In a modern inspection environment, verifying this geometry relies on model-based GD&T. Quality control teams use optical laser scanners to generate a point cloud of the manufactured part. The software then aligns that physical scan directly against the true profile of the original CAD model, generating a color deviation map to show exactly where the surface passes or fails. Because CNC machines and 3D printers run on coordinate data, they easily follow these true profiles. Manual machining, however, often struggles to accurately replicate nonlinear shapes without specific tooling. When drafting, a common mistake is selecting a position tolerance to control a complex surface. Position is intended for features of size like holes or pins. When you need to control the functional boundary of an actual surface, profile is the correct tool. Another frequent error is over-constraining the part. If a curved feature only needs to have the correct basic shape to function properly, adding datums to the feature control frame will force the manufacturer to hold tight locational tolerances that aren't actually necessary. Finally, designers sometimes rely on general linear dimensions to locate curved features without defining the exact shape and size of the tolerance zone. This creates ambiguity on the manufacturing floor and disagreements during inspection. Profile of a surface bridges the mathematically perfect world of your CAD design with the physical realities of manufacturing and inspection. When applied correctly, it ensures your complex geometry is built exactly as intended.